For one, let me start off with some formulas, which in case they weren't clear or you don't already know what they are, here's a formula for the mean of a set of n numbers. You add them all up and divide by how many of them there are. You probably have known that since like 4th grade, but maybe you don't know the variance formula. So once you've found the mean of those numbers, you can then find their variance. And this is the formula for their variance. It's pretty close to the average of the square of their distance from the mean, although not exactly. It's not exact because of the fact that there's an n-1 and not an n right there. And there's a good reason for that, although I don't have time to get into it now. But finally, once you've calculated the variance, you can then simply take its square root to get the standard deviation. So the standard deviation formula is just the square root of the variance formula. Okay, so here's a few other vocab words. The median of this set of numbers is their 50th percentile. That means the data point such that 50% of the data is below that point and 50% of the data is above it. If you have an even number of data points, well, in that case, you just take the middle 2 data points and take their average. Another point about the median is it sometimes helps to sort your data in increasing order in order to find the median. Then, once you're able to find the median, you can find the first quartile. That is simply the median of all the data that's below the original median of the data. In other words, i.e., Q1 is the 25th percentile. Similarly, the third quartile, Q3, is the median of all the data that's above, well, the original median of the data, i.e., Q3 is the 75th percentile. And we can then define the interquartile range as Q3 minus Q1. This is another measure of spread. So the standard deviation and the interquartile range are both measures of spread of the data. The larger they are, the more spread out the data is. On the other hand, the mean and the median are both measures of center of the data. So let's try an example. How about for the interquartile range of the set 1, 2, 3, 4, 5? So first, I need to find the median. Well, in this case, it's not so hard because, for one, the data is already arranged in increasing order. Secondly, there's an odd number of data points, so I simply need to pick the point right in the middle. In fact, the median is also the same as the mean of this data set. So in order to find the interquartile range, we're going to need to find the first and third quartile. The first quartile is the median of all the data that's below the median. So the data that's below the median is 1 and 2. Hence, the first quartile will be the average of the numbers 1 and 2. Which is 1.5. The third quartile will then be the median of the numbers that are above the original median. That is to say, it's the median of the data set 4, 5. And since that's an even number of numbers, I simply take their average. So it'll be 1/2 of 4 plus 5, which is 4.5. Thus, I can now calculate the interquartile range as the difference between the first and third quartile, Q3 minus Q1, which is 4.5 minus 1.5, which is 3. Okay. Oops. Make this a little bit nicer. For my next example, the challenge is to find the standard deviation of all the integers from 1 to 2021. And I'm not going to do this here now. I'd like you to try it. And I'm going to do this one in class. But by the way, you are intended to do this by hand, okay? You don't need a calculator. You don't need a computer. You will need some formulas. So you know what? I'll give you a hint. How about? So I'd like you to try this one out, but just to help you, here's 2 formulas that may be helpful. The first one is that if you add up the integers from 1 to n, there's a formula for that. It's n plus 1 over 2. And if you add up the first n squares, see, what the heck is that? That's n plus 1, 2n plus 1 over 6. So those 2 hints will help you. Why don't you try that out? And I'll talk about this one in class on Wednesday. Moving on. Now, I'm going to talk about some things that are not in the textbook, at least I'm pretty sure they're not. So here's some R coding language that will be helpful. It will be useful. So R stores lists of numbers as a vector, and there's a few ways that you can create them. One of them is with the concatenate operator. Basically, anytime you want to create a vector, just write C parentheses and then the entries of the vector and end parenthesis, and that's how you can create it. So in these 2 lines, I actually wrote it 2 different ways, one of them with an equal sign and one of them with this replacement arrow. Either one works, okay? You can use the equal sign or the left pointing arrow. Both will be fine. And in both cases, by the way, I'll just tell you what this does. Whether you do the first one or the second one, in either case, this makes the list of numbers or the vector 17, 42, 3.14. Now, here's another way to create a list of numbers using the colon operator. And this just creates a list of consecutive integers, starting at the first one and ending at the last one. So, for example, if I defined my vector 2 to be 2 colon 17, well, that's going to make a vector or a list of the numbers from 2 to 17. So this one makes, it'll be 2, 3, 4, ... all the way up to 17. So that's handy. You can also do a similar operation using the sequence command. And the sequence command also, additionally, it allows you to specify how much you increase each element by to get to the next one. So if I wanted to create another vector using the sequence command, let's say I want to create the sequence which goes from 5 up to 20 by intervals of 5. So this one is going to make, well, it started at -5, and we're going up by 5s. So -5 plus 5 is 0. Up by 5 again is 5. Up by 5 again is 10, 15, and then all the way up till 20, because that's what we said we were going up to. So let's try some examples. For my next example, I challenge you to write some code to make the set from -3 up to 3. All the integers from -3 to 3 inclusive, and see how many different ways you can do it. I gave you 3 approaches. Why don't you pause the video at this point and try to do this yourself? Use each approach, and you know what? See if you can even come up with any additional approaches. So let's see. We could use here's the answer. I'm assuming that you've unpaused the video at this point after already having figured it out yourself. So if we used the concatenate operator, we could have just, let's see, what do we want to call this? How about my vector 4? So we can use the concatenate operator and concatenate -3, -2, -1, 0, 1, 2, and 3. So that would be one way to do it. Another way to do it, how about using the colon operator? In that case, we could write -3 colon to 3. So if you type -3 colon 3, that will create this vector. I gave it a name right here. And in fact, you don't really need to give it a name for this purpose. You only need to give it a name if you want to use it for something else. And that's something that you'll discover as you start investigating R. But let's just give it a name since I already did that. So we could say my vector 5 is that. And a third way to do it would be using the sequence command. So let's let my vector 6 be the sequence starting from -3 going to 3, and we are increasing by 1 with as we go from entry to entry. So that would be 3 different ways of creating this. And as a fourth way, how about this? What about my vector 7 equals the sequence from I could do the sequence, let's say, from -2 to 4, and then subtract 1. And you know what? Why don't I check my answers? So here, this is going to be embarrassing if I got any of these wrong, but let's go over to R. Oh, which means I got to share a different window. Okay. So now here we are in R Studio. Let's create my vector 4 is the numbers from -3, -2, -0, 1, 2, 3. My vector 5, that is also the desired sequence. My vector 6, in fact, yes, that is also the desired sequence, -1, -2, -1, 0, 1, 2, 3, or my vector 7, that is also the sequence from -2 up to 3. So all 4 of those methods worked. Great. Let me now share OneNote. Oh, okay. So example 4 is me asking you to write code to check the answer to example 2. Now, I didn't do example 2. Example 2, if you forgot, was the standard deviation of the numbers from 1 to 21. But you know what? I'll write code to check the answer, just so you can find out if you did it right, if and when you figure out example 2. So let's go do this one in R. How about? So let's see. Let's call this vector years. And years is going to be the sequence of integers from 1 to 2021. Okay. And I want the standard deviation of that sequence of integers. So let's take the standard deviation of years. And what do we get? 583.556. So let's just paste this into OneNote. And there's the answer. And when you do example 2 by hand, you should get the same answer. Finally, we have example 5. So according to the box plot definition in the text, if you watch the earlier videos carefully or read the textbook, they define an outlier as any data point that lies outside of the fences. These fences are defined in the definition of a box plot. So you've got your upper fence, which is 1.5 times the interquartile range above the third quartile. You've also got your lower fence, which is 1.5 times the interquartile range below the first quartile. Oops, there's a little typo right here. Sorry. So here's some summary statistics from the census data, which I've made reference to in earlier videos. You can see it has a minimum of the total personal income. These are summary statistics for total personal income. It also has the first quartile, the median, the mean, the third quartile, the maximum. Apparently, there's a few data points which were not available. Don't worry about those. So, question, does this data set appear to have any outliers? And you know what? I'm going to do this one in class too. I'm sorry. I know you probably wanted to see it. I want you to try it. So I will do in class on Wednesday. It's a little bit tricky. You're going to have to construct the upper fence and then see if, see if you have data points that lie above it. So you're going to have to construct the upper fence and consider this maximum personal income. And I will also talk about whether this is likely to be skewed. So I want you to think about these questions, see if you can do it yourself, and you'll see if you get it right when we get to class. Okay, that's it, folks. Thanks for watching. Goodbye. Okay, so example 2 is this one. The problem is to find the standard deviation of the numbers from 1 up through 2021. And I gave you 2 hints or 2, I don't know, semi-obscure formulas. Maybe you remember them, maybe you don't. But they're the sum of the first n integers and the sum of the squares of the first n integers. So let's do the problem now. In order to find the standard deviation, I'm going to need the formula for the standard deviation. which is right here. In order to employ the formula for the standard deviation, it looks like I'll need to find the mean first. So I guess I better start out by finding the mean. Can anyone guess what the mean of this sequence should be? Like just by looking at it, even without doing calculation? James?
1010?
Okay, yeah, because that's like right in the middle. It's kind of a symmetric structured sequence. So that's a good guess. If, by the way, we considered this set to be the set x1, x2, up to x2021, then apparently xi is just equal to I. The ith element of the set is equal to I, where the index ranges from 1 up to 2021. So that's the x sub I that I'm going to plug into the formulas for the mean and the standard deviation. So as I said, I'm first doing the mean. So I need to add up all the values and divide by how many of them there are. So let's see, there's 2021 of them. And adding them all up means 1 plus 2 plus ... all the way up through 2021. And I'm going to write that with summation notation. If someone has a question on the summation notation, let me know. So I could write it using summation notation as well, just the sum of the first 2021 integers, which means we can use this formula right here. So let's just plug in that formula and see if we get the answer that we expected to get. So according to that formula, we're going to get, let's see, n times n plus 1 over 2, where this is your n. So I'll get 2021 times 2022 over 2. Cancel. And what is that? Oh, 1,011. The number right in the middle. Okay, good. I think that was our guess, right? Now that, so a comment, notice that like we had a guess for what the mean was, but we now just verified it mathematically. This is going to help on the homework, by the way. Scott?
If you get a chance this lecture, can you go over why the book is using the convention of 1 over n minus 1 instead of just 1 over n?
Yeah, sure. That's an interesting question. Okay, yeah, I'll talk about that after I finish the problems. But yeah, that's a fun topic. A bit beyond the scope, a little bit beyond the scope of this class, but I can still talk about it. Okay, so I can now proceed to calculate the standard deviation. I will first find the variance, and then I'll take its square root. So the variance is going to be, okay, this is going to be a long equation. It'll be 1 over 2020 times, let's see, 1 minus 1011 squared plus all the way up to by the way, here, let me just write the formula. It's 1 over n minus 1, sum from I equals 1 to n of xi minus x bar squared. So I'm going to arrange the terms. I'm going to write the first half of the term and then the second half of the terms. And that's going to help me simplify this big expression, because the point is to try and do this by hand, totally by hand, up until maybe the last step. So the first half of the terms would be where I goes from 1 up to, let's say, 110. Or 1010, I should say. The term in the middle is just 0. See, the next term will be 10, 12 minus 1011 squared. And the last term will be 2021 minus 1011 squared. Okay, so notice that, for example, like the first term right here, what's that? That is 1010 squared. This term here, what's that? That's 1 squared. Then we've got a 0 squared right in the middle of this long list of terms. Then we start increasing again back to 1 squared. This last term is back to 1010 squared. So the first, that 1010 terms is the same as the last 1010 terms. And the middle term is just 0, by the way, so I can just kind of ignore that one. So since the first half of the terms is the same as the second half, I'm just going to write it once and multiply it by 2. So let's write this as 1 over 2020 times 2, and then just times the sum from, let's see, 1 squared plus 2 squared all the way up to 1010 squared, which I could write with summation notation. That's sum of the first 1010 squares. And now you can see why I gave you that other formula for the sum of the first 10 squares right there. So let's apply that formula. And now we see that what I was calling n is 1010. So according to the formula, we're going to get 2020 times 1010 times 1011 times 2 times 1010 plus 1 all over 6. And now I get to do some cancellation. Let's see, I think this fraction will cancel with that. So I get 1011 times 2021 over 6. So I can just take the square root of that, and I'll have my standard deviation. So SD is apparently here. Let me type it out actually.
Standard deviation is apparently 1011 times 2021 over 6. And let's see what this is. This is 583.55677. So we found our answer. And yeah, I know I used the calculator there at the end. I mean, I could have just left it under the square root sign, but that's what I meant when I wanted you to do this by hand. So any questions on this one?
Could you scroll back to the definition of the standard deviation really quick, the general one?
Yeah. That's this here.
Thank you.
And also to everyone who watched the video, you know that I calculated this in R. It took about 2 seconds. And in R, if you just plug in standard deviation of the sequence, you get the same number. Where was that? Yeah, right here. So thus confirming our answer. The exact same number. Okay, so the other example I was going to do was example 5. And I'll do that now. So example 5 was about box plots and box and whisker plots. If you read the textbook or watched the video, they gave instructions for how you construct a box and whisker plot. You have to find these things called, well, I call them the fences because that's the term I've usually heard. The book looks like it calls them the max whisker reach. I think fences sounds better, but so let's call that the upper fence. And you find it by finding the third quartile and adding 1.5 times the interquartile range. Right, so the upper fence is equal to the third quartile plus 1.5 times the interquartile range. This picture, by the way, is not the data from the problem. This picture is the data, this picture is from the textbook where they explain box and whisker plots. Okay, so in the problem at hand, let's see, we're given what the quartiles are. So I can find the interquartile range. Let me do that first. The IQR is the third quartile minus the first quartile, which is 37,000 minus 5,900, which is 31,100. Okay, then we can find the upper fence. So apparently the upper fence is Q3 plus 1.5 times the IQR, which is 37,000 plus 1.5 times the IQR that I just found. So we get 83,650. That's the location of the upper fence. That's not the upper whisker, by the way. Oh, someone tell me, how do you find the upper whisker? found the upper fence, but the upper whisker is this line right there. What the heck is that?
Isn't it the max point that's under the upper fence?
Good. Yes, very nice, Axel. That would be the biggest data value that's below the upper fence. Okay, so in this problem, I only supplied you with the summary data. Like, you're meant to do this only using this summary data that I gave you. And I asked if the summary data gives us enough information to at least say whether there's any outliers, according to the definition of outlier as points outside the fences. Outliers are usually marked with dots or maybe little X's in box and whisker plots. So do we have any point that's bigger than the upper fence? Indeed, we do. The maximum of the total personal income, which was 456,000. So since 456,000, which was the maximum personal income, is greater than the upper fence, there's at least one outlier, right? Namely that maximum value. Maybe there's more, but there's at least one. So that is why the answer to the first question that I asked is yes. I also asked if the histogram is likely to be skewed. So let me mention a fact which maybe you picked up on. If the mean of a set of numerical data is greater than the median, then this usually, not 100% of the time, but usually indicates skew. Oh, in fact, if anyone's interested, I can provide a link to an article that has some counterexamples to that. So if you're interested, I guess that doesn't show the address. Here, I'll clean that up in post-production, but that's a PDF where you can see that there are occasionally counterexamples to this, but usually if the mean is greater, that indicates the data is skewed to the right. So hence, or I should say, since our mean, which is 29,000, is greater than the median, we suspect that our data is skewed to the right. So that's why the answer to the second question is also yes. Now, I finished the problem. I'm done. The answer to both questions was yes, but how about I verify some of these answers with R? So in fact, I already did this. I'll just show you the results. So let me show you the actual box plot and histogram. The box plot will show us outliers. So let's see, where did I have it? There's the box plot. So this is the actual box plot. I also showed you the command for how to do a box plot in R. Pretty simple. You just use the box plot command and then punch in the column with the variable of interest. And you can see that indeed it has a bunch of outliers above the upper whisker, and the uppermost, the one at the top, would be the one that corresponds to the maximum value that we mentioned. Moreover, let me show you the histogram. So here's the histogram of personal income, and it indeed is skewed as well, skewed to the right, thus verifying what we suspected to be true. Okay, that's it.